choosability with separation for planar graphs, but we couldn't do it for all planar graphs, so we put in some forbidden cycles. So this is joint work with Bernard Lissitzky and Derrick Stolle. When we started the work, all three of us were at Illinois. I was a student and 2 postdocs, but now I'm a postdoc here in Korea, and both of them are professors at Iowa State University. So I'll start with a list assignment because I want to define a refinement of list coloring. So everybody probably knows what it means for a graph to be k-choosable. A graph is k-choosable if for every list L where at each vertex you're guaranteed some k colors, not necessarily all the same, that you can do 2 things. 1, you can choose a color for each vertex, and 2, if you look at each edge, then the endpoints of the color, you can choose colors so that the endpoints receive distinct colors. So now I want to put in one more parameter into this, and this is not my idea. This is actually an idea by Kratochvil, Tuza, and Voigt back in '98. So they put in a second parameter, and they said a graph is KD choosable if you put in an extra assumption that if you look at the list assignment, that if you look at every edge, the intersection of the 2 lists of the endpoints are at most D. So hence the D here, right? So so instead of looking at graph classes that are k-choosable, you fix some graph class and you want to see how far you can push D. So for example, if you look at this graph K4, we know this is 4 choosable. But if you restrict the intersections of adjacent lists to be at most 1, then you can also show that it's 3-1 choosable. So for example, if I let this list be ABC, and if I look at the adjacent lists, I'll say, oh, these 2 vertices, the lists share the color A. For here, they also share A. And for here, they only share B. And I give it some other colors so that the list assignment is satisfied. So you can check that every vertex has 3 colors, and the intersection of adjacent lists is at most 1. Then you can choose a color for each vertex such that it's L colorable for the given list assignment. I mean, of course, you have to check it for all 3-1 list assignment, but this is just one instance of it. But what you can deduce from this, or some basic observation, is that every graph is 1-0 choosable, because the second parameter is the size of the intersection. So if your intersection size is at most D, that means that for every edge, the 2 lists are disjoint. So that edge in between is useless, right? So you might as well just delete that edge. That edge does not act as a constraint anymore. And if at every list, if you have 1 color, then you can you can choose that color, right? So every graph is 1-0 choosable. And if you look at a graph that's KD choosable, and if you increase the first parameter to K prime, then it's also going to be K prime comma D choosable, because you're just giving that list more available colors. And if you decrease D, so if you let D prime be at most D, then it's also going to be K comma D prime choosable, because you're not looking at all the list assignments. You're looking at a smaller set. You're looking at a subset of these list assignments. So one thing you can do is you can say, okay, so for each vertex, you're not going to give, for each vertex, you're going to give some number of colors that's strictly less than the list chromatic number. Because if you give each vertex the list chromatic number colors, then it doesn't matter what the second parameter is. You can always pick a color for that vertex so that you have a good L coloring. But if the number of colors is strictly less than the list chromatic number, since we know that every graph is K comma 0 choosable, and it's not going to be KK choosable, because since your K is strictly less than the list chromatic number, there's going to be some threshold where it jumps from being where it jumps from being choosable to not choosable. So this is the idea. The idea is, instead of looking at a different graph class, you're going to maintain your graph class, and you're going to look at what type of list assignments such that you can pick an L coloring. So I'll let this number, chi of L of G of D, be the minimum K where the graph is going to be KD choosable. So an example is the complete graph is n choosable. And this is just the same thing as saying the complete graph is n comma n choosable, because if the second parameter is the same as the first, then it's not a constraint anymore. So in their first paper by Kratoval, Tuza, and Voigt, they prove that, okay, if you look at the complete graph, and if every pair has only one color in common, or the lists have, adjacent lists have one color in common, then you don't need n colors at each vertex. The growth rate is approximately square root of n. So the complete graph is going to be something like the square root of n plus some smaller terms, comma 1 choosable. And then they conjecture that they have some conjecture where you generalize this 1 to d, and this was actually proven, well, it was proven 3 years ago, but it was published this year by Freddie, my advisor Sasha, and Mohit, one of Sasha's students. So they generalized this result by saying, okay, instead of that 1, I can replace it with a d. And then they give a further conjecture that if you look at these graphs, if you consider choosability with separation, the worst case is when you're the complete graph. So if you give me an n-vertex graph G, and if you look at the number of colors that are required for a graph to be something d-choosable, then the upper bound is, the worst case is Kn, your complete graph. And then they also have some result about complete multipartite graphs, and they also have some limits, and they consider the growth rate of these functions. So this is one end of the spectrum, because you're looking at very, very dense graphs. You're looking at complete graphs and complete multipartite graphs. But at the other end of the spectrum, you want to look at sparse graphs. And of course, everybody's favorite sparse graph is planar graphs. So Thomason in '94 proved that every planar graph is 5 choosable. But then there are these series of results that show that if you want your planar graph to be 4 choosable, it's sufficient to forbid some cycle where the cycle is small. So what this means is if you look at the graph class, instead of looking at all planar graphs, you look at the graph class of planar graphs with one forbidden cycle where that length is somewhere between 3 and 7. Then the choosability drops from 5 to 4. And then there's a whole bunch of results that show that, okay, if you forbid these cycles or these cycles or these cycles, the choosability drops further down from 5 to 3. And of course, this first row is a lie, because Alon Tarsi actually proved planar bipartite graphs are 3 choosable, but I can't have an infinitely many number of x's. So these are some results, right? So the goal here is, instead of looking at planar graphs, you look at a smaller subfamily of planar graphs to try to see which graphs are 4 choosable or 3 choosable. But now what we can do is we can shift gears and say we can look at choosability with separation. So we're going to fix the graph class to be planar graphs, and then we're going to find that threshold I had on the first slide. So since Thomason proved that planar graphs are 5 choosable, this is the statement that planar graphs are 5 choosable, or 5 1 choosable, or whichever number works for the second parameter. So now I can look at various numbers of k and d. Right? So if d is 0, because every graph is 1 0 choosable, it's going to be 4 0 choosable and 3 0 choosable. And if I look at that second column, when k equals 4, right, we know there exists a planar graph that's not 4 choosable, because Voigt, for example, constructed this planar graph that's not 4 choosable. But by easily modifying the lists of her construction, you can also construct a planar graph that's not 4 choosable. So these are some negative results, but there are also some positive results by Kratoval, Tuza, Voigt, who prove that every planar graph is 4 choosable. So this means if you give every vertex of a planar graph 4 colors, and if the lists of adjacent vertices have at most 1 color in common, then you can properly L color that graph. And then a simpler proof was given by Krakowski 3 years later. But it's still open. It's still an open question whether all planar graphs are 4 choosable or not. Okay. And I'll talk about this towards the end. So now we'll look at the first column. So the first column this is also a no, right? Because there exist planar graphs that are not 3 choosable, of course, because they're not even 4 choosable. But you can also modify the lists in this construction, and you can make sure the intersection sizes of adjacent vertices are at most 2. So they're also not 2 choosable. So another question is, are all planar graphs 3-1 choosable? And this was asked by Shkrekovsky. And the only known partial results were the ones by Kratova, Tuza, and Voigt, where they proved triangle-free planar graphs are 3-1 choosable. And the way they prove it is you can easily find some orientation where the out degree is at most 2, and if you just delete the colors among these edges or where you have this intersection, then by some easy argument you can easily color the planar graph. So this was the state of the art before we started working on this. And then what we were able to prove, me, Bernard, and Derrick, we were able to prove that we weren't able to prove the full conjecture, but instead of forbidding 3 cycles, we said, okay, what happens if we try to forbid other types of cycles? So we proved that the graph class of planar graphs with no 4 cycles is also true. It's also 3-1 choosable. And then we were able to prove that if you forbid 2 bigger cycles, right, namely you forbid 5 cycles and 6 cycles in your planar graph, then it's also going to be 3-1 choosable. So in comparison to this, right, this was the slide I had like 2 slides ago. If you want to guarantee 3 choosability, then all the known results or all the quote-unquote important results say that you forbid either one of the 3 or 4 cycles and then a couple more. But what if you don't want to guarantee 3 choosability? If you just want to guarantee 3, 1 choosability, then it's sufficient to forbid only this 4 cycle and the 5 and the 6 cycle. So these are not quite, of course these aren't comparable with these results, but it's just to see how 3 choosability and 3-1 choosability interact with each other, I guess. So, yeah. So I'll give a proof of this statement, but actually what we proved is we proved something slightly stronger. It's like Thomason's result of planar graphs being 5 choosable. Thomason actually proved that you can pre-color 2 vertices, and not all vertices need 5 colors, right? You can have the vertices on the boundary to have 3 colors. So we have some similar induction step. Right? And I'll give a short proof of this because it's neat. And the reason I want to show you this is that if you look at the proof, there's only 1 or maybe 2 places where we use the graph as triangle-free. Right? So we don't really heavily use the fact that the graph is triangle-free. So maybe this can be improved, but we couldn't see a way how. So what's the induction hypothesis? The induction hypothesis is the same. It's similar to Thomason's 5 choosable. Planar graphs are 5 choosable, or planar graphs with guard 5 are 3 choosable. You have 2 pre-colored vertices here. That's what number 3 says. And then number 2 says some vertices on the boundary have a list size 2. And then number 4 says these vertices must form an independent set. And of course, 1 means every other vertex has a list of size at least 3, and the 5th one means that adjacent lists have at most 1 common color. Right? So the first step you can do is you can remove all the unnecessary edges. Right? You look at an edge and you look at the 2 lists on the endpoints. If they don't have a common color, you just simply remove it because that edge is useless anyway. And then you prove that there are no chords. This is the same as Thomason's result, right? Because let's say your graph has a chord, you have your 2 pre-colored vertices. I look at this part, it's a smaller example, so by induction I obtain some coloring, and then I use that coloring to extend it to the other part. So now your graph has no chords. And then what I'm going to do is I'm going to pick a vertex on the boundary that has list size 3. And you know that always exists because the vertices of list size 2 form an independent set. So now you look at this, and now you have 2 vertices on the boundary adjacent to this 1 vertex you've chosen. And if this is the list assignment, then because your list assignment is 3, 1, there's only going to be one color that this vertex shares with the one on the left and one on the right. And since the vertex you've chosen have 3 colors, you can pick a color that's neither on the left one or on the right one. So the goal is you're going to color this vertex with this color. So I rip off that vertex from your planar graph. Right? So you rip it off, and then you remove this color C from the vertices that are adjacent to this vertex. Right? And once you do that, the list size will drop from 3 to 2. And you can use the fact that planar graphs are triangle free to show that these vertices form an independent set, but it's not actually necessary at this point. Because once you choose this vertex to have color C, and once you remove color C here, and if you remove color C here, then these two vertices will not have a common color in their lists anymore. Right? Because they used to both have C, and your list assignment is 3, 1. Right? So therefore, these two will automatically become independent after you remove all of the unnecessary edges. But maybe this will happen, right? Once you rip it off and you create a new vertex of list size 2, then maybe it will be adjacent to a vertex of list size 2 on the boundary. Right? And this is why we prove that there are no chords. Right? Okay, so the next idea is to show that there exists some vertex where you can rip off and you will not create some edge like this. Right? So how? Let's say I've chosen this vertex, and the idea was to rip this vertex off and remove this color. And maybe this vertex here is adjacent to a vertex of list size 2 on the boundary. Okay, so that might happen. So on the boundary, I'll look at a vertex on this side, and that vertex must have list size 3 because the vertices of list size 2 are independent. And then I'll try to rip it off again. So this will happen. And one thing to note is that this 2 chord, this chord of length 2, cannot cross over to this part, because once it does, it will create a triangle. And this is one part where we use that the graph is triangle free. But maybe this vertex, the new vertex you've chosen has a problem. So you look at this one, you go on here, you do the same thing, and then you keep on going. But you can't go on forever because it's a finite graph. And you know there's always a vertex here. There's always a vertex here onto the right side, because if there isn't, then if this is adjacent to this vertex, then it forms a triangle. Right? So there are only 2 parts where we use that the graph is triangle free. Right? So maybe this proof can be improved, but I have no idea. And the bad news is that this proof will not work as it is for all planar graphs, right? Because if you look at this one, this graph and this list assignment satisfies all the hypotheses, but obviously it's not 3, 1 colorable. And this one over here satisfies all the hypotheses, but it's not 3, 1 colorable. So there has to be some modification of the induction step, but I don't know how to do that. So this is how the proof works for 3, 1 choosability of triangle free graphs. And then similar technique works for 3, 1 choosability of C4 free planar graphs. But in this one, you only have to remove 1 vertex. And in this one, you have 6 cases. And depending on which case you're in, you might have to remove up to at most 3 vertices. And then a couple of pages afterwards, you can prove that it's 3, 1 choosable. So the next one is when you forbid 2 longer cycles, C5 and C6. And this one is done by some horrible discharging. And you have these 20 rules. But the good thing about this paper, and the reason I'm mentioning that, is that you have 20 rules, but we found a way to generate these reducible configurations. And so we started with 6, but then we quickly found out a way to generate an infinite number of reducible configurations. And we actually use this infinite chain of reducible configurations to show that it's 3, 1. So the statement is that if some configuration is reducible, namely if it can't appear in the minimum counterexample, then if it has one edge sticking out, then I can just replace it with this triangle, namely this configuration number 3 here. like this. So once you have a reducible configuration, by adding or appending these or replacing an edge with these triangles, I can generate many, many more reducible configurations, and this helps in the discharging process. So this is the state of the art. So maybe somebody can finish off these questions. And thank you.